Hello, everyone. We would like to thank you for assisting to the presentation of our work. Title is Fake News Detection. Do complex problems need complex solutions? This is a word that has been formed by Ignacio Palacio from the University Autónoma de Madrid and David Arroyo from the Spanish National Research Council. I hope you enjoy the presentation and you find interesting the work we have performed. Here's the detailed structure of the presentation you're going to see here and after. First, we will be delivering an introduction and motivation of our work. Then we'll follow with an examination of the used dataset and a detailed analysis of the information containing. After that, we will go to an analysis stage. We'll be presenting the NLP techniques, embedding-based classification architectures, and deep learning approaches. With the fourth stage on reporting, we'll be introducing the use reporting metrics and the results obtained. And finally, we'll be presenting our conclusions and work ahead. The expanding exposure to fake news affects the way people approach and respond to real news, undermining their capability to separate facts from fiction. It is important to understand that even though fake and captious news have existed from long ago, we are witnessing an overwhelming increase of false information, and we are increasingly exposed to information operations and personalized campaigns of false information. The outstanding increase of false news is not only a problem of misinformation, but one of the greatest threats to democracy itself. Examples of such are the 2016 US presidential election campaign and the 2016 Brexit referendum. This erosion of democracy and public trust has led to a sustained demand of further analysis of this phenomenon as to newer regulation. Regarding the dataset information, we've used the data provided by Kin et al. On their homogeneity-based transmissive process to model true and false news in social network. Such information is available on GitHub. From the stories information in the tweets, they excluded those news whose content could not be retrieved, cleaning the stories cascades and confirming that there were no circular retweets. The figure in this slide provides detail on the data layout. After all preprocessing, the original dataset contained almost 1,200 tweeted stories divided into 4 labels. For the purpose of this work, we reduced the existing labels into just 2 categories. Unverified tweets were discarded and true and non-rumor labels were tied together into a single category. For each resulting label, true or false, the following figure presents the number of stories in the dataset in terms of their number of words or content size. After label cleaning, the resulting dataset is divided into 660 true stories and 262 false stories. A bias in the used dataset was identified as it has below 30% of false stories. Three natural language processing algorithms are presented to address the fake news classification problem in hand. First of them is the term frequency versus document frequency (TF-IDF) algorithm. And then there are two embedding algorithms, namely word2vec and doc2vec, which create mapping vectors for words in the corpus of every document user in the dataset. They take both of them, both embedding and TF-IDF. They take the pre-processed stories and are followed by traditional machine learning classification algorithms to classify the Twitter stories into true and false stories. This slide demonstrates the structure of the architecture developed for the NLP techniques, where we have a first stage of natural language processing text management in terms of text lemmatization, stop word removal, cleansing of all kind of punctuation, spaces, and so on. There's a second layer or three kind of algorithms of natural language processing classic techniques were implemented, which are mainly, as said before, TF-IDF, word2vec, and doc2vec. And there's a final layer of machine learning classification algorithms namely random forest, extreme gradient boosting, k-nearest neighbors, and support vector machine, where all NLP techniques are fed into these four machine learning classification algorithms, and those algorithms are the parameterization is grid sorted 14 parameters that are shown in the provided table. In terms of deep learning approaches, two architectures were tested: long short-term memories and gather recurrent units. Here you can see comparison between both neural network implementation and the brief schematics on their implementation, and we present as well the long short time memory grid subject parameters with all tuned parameters and the values that were tested in our implementation. On all classification algorithms, both AUC and accuracy metrics are used to calibrate the grid searched parameters. Regarding accuracy, in binary classification, it is used as a statistical measure of the goodness of a classification, testing how correctly it does identify or exclude a condition. It defines the proportion of true results over the total. Besides, the area under the receiver operating characteristic curve (AUC) provides visualization of true positive rate against the false positive rate. For the considered deep learning approaches, close validation was carried out using a tenfold stratified k-fold, and further tuning by means of data augmentation, hyperparameter grid search, or k-fold validation did not provide relevant improvements. In this slide, you can see the statistic in terms of both scores, accuracy, and AUC for all tested architectures, including natural language processing techniques, all combined, both TF-IDF and embeddings, all combined with all four machine learning approaches, as well as the deep learning approaches, which are presented in the plot as the two last categories. Best obtained return results were in fact a little below a 93% of accuracy and a little below an 88% of AUC for TF-IDF combined with a support vector machine. TF-IDF and Doc2Vec provided better results in general terms than Word2Vec and all tested deep learning implementations. The obtained results demonstrate somehow that traditional NLP approaches, even represented old-fashioned techniques, still worth trying, especially when available data is scarce. Best architecture for a certain problem might highly depend on the task in hand, especially taking into consideration the high complexity related to deep learning approaches, hyperparameter tuning. In our experiments, we have performed a selection of the most suitable solution for the considered dataset. We have concluded that the simple model based on TF-IDF and a support vector machine determines the best score. This can be considered as an evidence on the high importance of the size of the dimensional space provided by the available data. The obtained results, however, do not draw definitive conclusions but are merely indicative of a possible trend, since further testing should be performed to confirm the ground basis. A single dataset was used and a limited set of algorithms was tested, and further analysis, especially on deep learning techniques, including a deeper range of data should be performed to confirm the present results. Nevertheless, the outcome of this communication raises some concerns regarding deep learning training, the computational cost associated with the hyperparameter tuning, explainability problems, and the urge to consider all these problems as a whole when discussing the approach to be taken for a specific application and context. Thank you all very much for attending our presentation.